Hello again, this is Dr. James Camp from Lee College in Baytown, Texas, and these are my comments on Part 2 of Chapter 8 from Big C++ by K. Horstmann. We're going to be talking about some miscellaneous stream stuff, string streams, command line arguments, and binary files. So, if we want to extract numeric information held in a string, we can adapt the string to have the same interface as stream types. Okay. Then we can use the greater input and less output operators on the strings. We have a couple of classes called istringstream and ostringstream that do just that. You need to pound include the s-stream header to use these. So if we declare a variable of type istringstream, that allows us to read data from a string as if we were reading it from CN or from a file stream. So we declare the variable istringstream and we call it strum. Okay. Then strum.str string, and then we pass it the string we want it to interpret. Then we can say strum greater month, greater day, greater comma, greater year, and that will pull all the information we want out of that stream. In C++11 and later, which is what I assume all of y'all are working in, you can use the functions s2i and s2d. I believe those are from the string header. So if you have only a single, if your string is only a single value that's a number, you can convert it to an integer with s2i and into a double with s2d. There's also an ostring stream that copies text and numbers into a string. Okay, so this is for formatting output and making it into a string. So we create an ostring stream strum, and then we use the output operator to put the month and then the day, a month and a slash, and the day and a slash, and the year, and then for some reason we decide to add 10 divided by 3 to the output. And that will give us a string with, because we chose to set fill 0, we'll have 01/24/1973 and then dash 3.33333. To get a string out of a string stream, we call the .str function, member function, just like we call .str on the istring stream. To input a string, we're calling str on an ostring stream to output the string. If you don't need formatting, you can use the C++11 toString function to convert a single number into a string. So if we wanted, if somebody had given us the month as a string, July, but the day is an integer, and we wanted to convert that into July 11, we could, as a string, we could say toString parens day, and that would do the trick for us. As a bit of a practice run for you, you can try completing this function here, which is supposed to take an address such as Houston, Texas 77004, and return a vector of strings with each of the words as its own part of the vector. So you would extract Houston, remove the comma, extract Texas, and then extract 77004. Okay, command line arguments are a little bit harder idea to wrap your mind around because most of us don't use command lines anymore in our day-to-day interactions with computers. But let's get some background on this to see where this idea comes from. Depending on the operating system, whether you've got Linux or Windows on your computer, for example, or Mac OS, and the C++ development system that you're using, there are a couple of different ways to start a program. You can select Run in the compilation environment. If your IDE has a little Run button, that's usually the easiest way to test your program. You can compile the program and then double-click its icon, or you can type the program name at a prompt in a command shell window, which is the most common way of doing things when you're doing Unix programming, or Linux, or that sort of thing. To get a command shell in Windows, you type command in the search box, and then choose command prompt or cmd.exe. This is in Windows 7, 8, 9, 10. There wasn't a 9, was there? Never mind. 7, 8, 10, or 11. On a Mac, you go to your applications and then utilities, and you choose terminal, and you get a command prompt that looks a lot like this. In Windows, the command to change directories, a directory is an old-fashioned word for a file folder, is CD, and so I move to source, repos, print calendar, and then I want to see what's there, so I type dir for directory, and I hit this. I type /w to get a wide listing, and you see I've got a print calendar folder and an x64 folder that's going to contain my executable. So I go to cd x64/debug, do another dir, and I get printcalendar.exe. Now in Windows, every program that you can run is an executable file. It ends with a .exe. So I know that that's where I want to be to run my program. I don't type the .exe though. I just type the name of the program. So I type print calendar, and this is a cute little program I wrote that asks how many days are in the month and which day of the week it starts on, and it prints a little calendar. You see, that's how you would start a program from the command line. Now, in the old days, when C++ was developed, all programs were started via command line. The command shell would start your program and then pass any command line arguments like the /w to make your listing wide to your main function. So main had to be defined a little bit differently. It looked like int main, int argc, that's the count of arguments, char star argv, that's a vector. It's not actually a vector, it's an array, but a vector of command line arguments, of little strings, C strings. Okay, the first parameter is the number of arguments, and the second is an array of C string pointers to the various arguments that the user typed. Now, everything the user typed gets passed along to main, so argv of 0 is always the name of your program, and argc is always at least 1. So let's see how print calendar works again with command line arguments. I type print calendar-help, and I get this cute little calendar printer v0.1, and then in a box it tells me the correct usage is to type print calendar and then the number of days and then the start day. So I try this again. I type print calendar 31/6, and look, it gives me the beautiful calendar that I was asking it to print, without having to do any input from the user at all. I don't have to do any cin statements to get that 31/6. Here's how I made that work. Okay. I said if argc equals 3, then in that case the user typed the exact correct number of arguments. Then if the first argument at the first position is a digit, then I'm great. I've got how many days. Otherwise, I print the help string and I quit. If the second argument in the first position is a digit, then yay, I've got the start day 2. Otherwise, I print the help message and I quit the program. If argc is 1, then the user didn't type any arguments, so I go into what we call interactive mode. I do the cout to prompt the user and the cin to get the information. And then I say else, if the user typed the wrong number of arguments to start with, I print the help message and return 0. Okay, so as you can see, you can use command line arguments as an alternate way to give a program input. Okay, other common uses are to specify program options. For example, -v tells a Unix program to give verbose output to show you more information than it normally does when it's doing its job. Also, we often use command line parameters to specify input or output file names. So if I did prog-v input.dat, that means run program prog, tell it to print verbose output, and then tell it to take input from a file called input.dat. So if the user typed prog-v input.dat, argv is going to be argv at 0 is going to point to the string prog, argv at 1 is going to point to the string -v, argv at 2 is going to point to the string input.dat. Okay, and I think that really is about all you need to know about command line arguments at this point in your life, because most programs that we write don't use them. But it's cool to know how, just in case you ever do have to write a program for, say, a Linux programming class that you have to take, or something like that. Or if your boss, heaven forbid, likes using command lines and wants you to write a program that does that. Okay, sequential access and random access. Sequential access is what we've been doing from the beginning. You take one input at a time, you start at the beginning, and you move through the file in sequence. Random access is where you can go immediately to any point in the file by specifying a location to jump to. Now, file streams support this, but cin and cout do not. In fact, it kind of defeats the purpose of treating input as a stream to be jumping back and forth to all these different places. But it is something you can do. The way you do this is you use the put function to tell it where the next write will go, and the get position to tell it where the next read will be. And to position those, you call seek G for seek get and seek P for seek put. Now, why would you do this? You would do this because you're working with a binary file. Okay, recall that all data, including text files, are really binary files. They're stored as ones and zeros in computer memory. Okay, so my initials in a computer file would actually look like this string of ones and zeros right here. Now, we tend to deal with computer data in files in bytes, units of 8 bits at a time. So we could break that series of bytes up into, or that series of bits up into 3 bytes here. And if we then tell the computer that that's a text file and we're supposed to interpret those as ASCII characters, we'd get the letters J, P, C. but we don't always want to interpret the files as ASCII characters. Sometimes we have non-text data, okay, like an image or a sound, or a carefully formatted term paper, which has a lot of text in it, but it also has computer symbols indicating where the text is supposed to be bold, where it's supposed to be underlined, where it's supposed to have a table of contents entry, and where it's supposed to have a figure inserted. Okay. All of those things can be stored as binary data in a binary file. Let's take a color image, though, as an example here. A color image is a series of pixels, okay, each of which has a red, a green, and a blue color value. If we allow 8 bits per color for what's called 24-bit color, we end up writing 3 bytes to the binary file for each pixel. Okay. The binary data in an image file has a special meaning to any program that knows how to read it, but if you were to just open it in a text editor, it would look like a bunch of gobbledygook. Okay. Instead, we have to call stream.open and tell it specifically that this is an ios : binary type file. Okay. And we can't use the stream input operator to read a binary file. We have to read 1 byte at a time by calling the get function, stream.get. Now, if you're reading integers, you have to do 4 reads because integers are 4-byte numbers. Okay. We're going to look specifically at a program in what's called the bitmap or BMP image file format with what's called 24-bit true color. Okay. Each pixel's picture element, okay, is represented in a red, a green, and a blue value. They're actually written backwards. They're written a byte for blue, a byte for green, and a byte for red. Now here are just a couple of examples of how colors work in RGB, or BGR as it is in BMP files. Cyan is equal amounts blue and green and no red. Red is no blue and no green, but all red. A gray would be equal amounts of all 3. Binary files start with a header. If you ever get into really working with binary files, then you can learn more about that. But basically, at specific byte locations, there are specific things that you can look up, like the width and height of the image. So the image itself comes after the header, and it's written in a BMP file in a whole series of what are called scan lines, individual rows of pixels that make up the image. Scan lines end with just enough padding bytes to make the whole line divisible by 4. I'm not sure why they chose to do that, but they do. So if you had 9 bytes for 3 pixels, you'd need 3 more padding bytes to make the whole thing 12, which is divisible by 4. Okay. Now our job in this coming program is to simply invert an image, turn all the darks to lights and lights to darks. We do that by subtracting the R, G, and B values from 255. So we start by writing an invert function, which takes blue, green, and red pixel values as references and simply subtracts each of them from 255. Then we have a getInt that's used for reading the header. You can see that we have to read 4 pixels and multiply them by a base value so that we can add the whole thing up to make a full integer. Then we simply get int for the file size, the start, the width, the height. We do some basic calculations, and then we seek the start. Okay, and we're doing a seek G because we're getting ready to get. Okay, and then for each pixel, we're going to read the pixel with a stream.get for blue, a stream.get for green, and a stream.get for red. We're going to invert the blue, green, and red values, and then we're going to seek back to the position of the pixel and write the blue, green, and red values. Then at the end of each line, we skip the padding bytes and then go back to, go on with the next line. Okay. A little practice you could do is to take that imagemod.cpp program and modify it so that instead of inverting the programs, it's turning every green pixel red, every blue pixel green, and every red pixel blue for kind of a psychedelic color effect. And really, you only need to change that one function from an invert function to a color modify function. Okay. That's it for this chapter. We'll be continuing on next time with object-oriented programming. So that's where the class gets really exciting. Until then, good luck and happy programming.